So it's without else. So thanks to the organizers for the invitation to speak, and special thanks to Marina for for making the Blackboard talk happen. So I'll begin by reminding you about Szemer's theorem on arithmetic progressions. Which was proved in 1975. So Szemer's theorem states that subset of the positive integers having positive upper density which means that when the suit of the density of that set in the first n integers is positive. So any subset of the positive integers with positive upper density contains arbitrarily long non-trivial arithmetic progressions. And that means configuration of the form x, all the way up to x plus minus 1 times I, giving a k-term arithmetic progression. And non-trivial means that y can't be 0, so that this is actually an interesting theorem. So can the people on Zoom read my handwriting?
Yes.
Yes, thank you. So this formulation of Szemer's theorem is equivalent by standard compactness argument to the following formulation, so that any subset, so I'll call it A, of the integers from 1 up to n, filtered out with these square brackets around n. That has no k-term arithmetic progressions. So these things. So without non-trivial ones. Must have size. Live level. Okay. And it's one of the central problems in additive number theory to determine the best possible bounds for this little O of n term. The important question. In other words, is what is the size of the largest subset of the integers of n without not trivial k-term arithmetic progressions. So Szemer's original proof of this theorem does, I mean, you can extract some explicit bounds from it, but these bounds are extremely weak. So the savings over the trivial bound of just n grows slower than any finite number of blocks. So we're most interested in, or we would like to prove, like what are called reasonable bounds for this quantity. So that meaning that k divided above by n divided by some function omega that goes to infinity. At least as fast. As a finite number of iterative logs. So log sub m is going to be the m-fold iterated logarithm, not the log of n to base m. So what's known about this? Well, we have reasonable bounds for all k in Szemer's theorem. So Roth showed in 1953 that when case 3, then any subset of integers 1 up to n without 3-term airtime corrections, bounded above by n over log n. We did this using Fourier analysis. But reasonable bounds weren't known. Oops, I forgot the 3. In Szemer's theorem for any larger k, until work of Gowers in 1998 for k equals 4, 2001 for k larger than 4. Showed bounded form n over some power of log n that depends on k. And in the course of this, he initiated a study of what's called higher order Fourier analysis. Which I'll tell you about later in the talk. So far I've mentioned 2 proofs of Szemer's theorem. There's Szemer's original proof. Then there's also Gowers' quantitative proof by a higher order Fourier analysis. Another very important proof is Furstenberg's ergodic theory proof. So Furstenberg in, I think, 1977. Is a proof of Szemer's theorem. Using ergodic theory. In which he introduced his correspondence principle. And his method has been adapted to prove very broad generalizations of Szemer's theorem. One of these, the one that will be the topic we'll talk today, is the multidimensional Szemer theorem proved by Furstenberg and Katz-Nelson. I think this was in 1978. So it says that we let S be a finite subset of C to the D, and because we also want it to be non-empty. Then if O is a subset of the n by n by n, so on, integer grid, and it has no nontrivial homothetic copies. Of set S. So that means sets of the form, a translation of a dilation of S with the dilation being non-zero. Then size of A is little o of entity. And it's a very interesting but difficult generalization of the problem of proving reasonable bounds in Szemer's original theorem to prove reasonable bounds for the multidimensional Szemer theorem. So getting some savings over the trivial bound of n to the d that grows at least as fast as a bounded number of iterated logs. So there are now, in contrast to some other generalizations of Szemer's theorem, there's now a general proof of the multidimensional Szemer theorem, not by ergodic theory. Okay, so there are, I think, now 3 proofs using hypergraph regularity ideas. But these, like Szemer's original proof of his theorem, give you savings over the trivial bound of like a Ackermann type. And right now, reasonable bounds are only known in one genuinely multidimensional case of the multidimensional Szemer theorem. So I mean something that's not like you take like a 3-term progression in 3 dimensions or something. I mean that's in the case of corners. Is the configuration x, y, x, y plus c, y. So when you plot this in 2 dimensions, this is what it looks like, where these side lengths are all z, and both z. And so this looks like a right angled corner. And this is, well, I don't have space to write this. So this is due to straight up.
I can see you've been in Germany for a while. This looks very professional.
Oh, thank you. Well, that means so much to me. So are there any questions about what I've said so far while I wait for this to dry a little more? So write down here that proof of reasonable bounds for subsets of the integers from 1 to 10 plus the integers from 1 to n were shown by straight up. This is the independent from 2006. Right, so who showed size of set second corners is found above 5 and over log n to some power. So this is, they said, the only case, generally multidimensional case of the multidimensional Szemer theorem for which reasonable bounds are known. So here are kind of the next two obvious configurations to try. So the next ones to try. So the next obvious thing to do is to add one more point to this corners configuration, and you can either add it in the same dimension that it lies in or in an extra new dimension. So if you add it in a new dimension, then you get 3-dimensional corners. So configuration form X, Y, Z, X, Y, Z plus W, X, Y plus W, Z, X plus W, Y, Z. And another reasonable one to try is axis line squares. So you just add the fourth vertex of a square formed by the 2 vertices of your corner, or the 3. So that would be the configuration x, y, y plus c, x plus z, y, x plus z, y plus z. But as of right now, it seems that proving quantitative bounds for sets lacking either of these configurations is like totally out of reach. And the main reason for that is, in my opinion, is that and when analyzing these two configurations, one thing that naturally arises is a 2-dimensional directional uniformity norm. So a uniformity norm in 2 dimensions. Arises, whose analysis seems completely intractable. And to even prove the 100% inverse theorem for this norm requires facts from group homology. And I'll also mention that the configuration of axis line squares is the subject of a question of Graham. So he asked whether if A is subset of cross C and the sum over all elements x, y of A of the reciprocal of x squared plus y squared. If this series diverges, then A must contain an axis line square. Okay, did I write this as a question? Yeah, I think so. Okay, so this question in particular also seems like totally out of reach. Because it's at least as hard as proving the four-term direction space irreducible conjecture.
What about the 3-point configuration?
So you can show that any 3-point configuration is basically either basically a one-dimensional configuration, or you can apply a linear transformation to make it into a 4-term.
Okay.
So yeah, good question. So we totally understand 3-point configurations and kind of don't understand at all 4-point configurations that aren't 4-term arithmetic progressions. So the focus of my talk today will be on a different 4-point configuration that we can prove quantitative bounds for. So a configuration I'll call L's. And this is another way of adding a point to a 2-dimensional corner to get a new configuration. This will be a configuration of the form x, y plus z, x, y plus 2z, y. So this is, you take the corner and then you add another point vertically to make it a 3-term arithmetic progression in the y direction, and then just another point with the same step size in the x direction. And so if you connect the dots, this looks like a capital L. That's why I call them L's. And I will give an outline or discuss a proof of quantitative bounds for sets lacking this configuration in the finite field model setting. And this will be the kind of first genuinely multidimensional 4-point configuration, for which we know bounds in any setting. If we let S be a subset of e to the n cross e to the n, assume that it has no non-trivial configurations of this form, so no non-trivial L's. Then the size of S, number both by n over some bounded number of iterated logs of n. Integer n. Okay, so some remarks about this. So the first is that, okay, I should tell you like how big m is. So I am working to make m smaller, but as of now, oh yeah, so I also need, sorry, I also assumed for my proof that p is sufficiently large, so it's bigger than some absolute constant. If you taking p to be at least like 23 works. So I'm trying to reduce m, but right now, with the proof I have, m is like 10 million, which I hope is a like record for logs in analytic number theory. So I think by optimizing the proof more, maybe I can get this down to 1 million, maybe even like 500,000, but there's like no chance I can get it down to like a 1-digit number of logs. But the same, so this argument, you should be able to adapt it to the integer setting. So it should be adaptable to the integer setting. And with much more reasonable so here, you can probably take n to be less than 10. And this is basically because Freddie Manners is inverse theorem for the Gowers norms. For Gowers norms of high degree, it's much quantitatively stronger than the inverse theorem of Gowers and Losevich that we know in the finite field model setting. So in the integer setting, we should be able to do like 1-digit number of iterated logs. So you should also be able to generalize the argument to other L-shaped configurations with L's with like a longer vertical leg, which should generalize. So to the configuration y, x, plus c, all the way up to y plus m times z, for any m, and then x plus c, y. But I don't think this sort of argument is generalizable to L-shaped configurations where you let the horizontal leg also be longer than just one extra point, basically for the same reason that proving anything about three-dimensional corners or axis line squares seems to be out of reach. If you end up encountering these like horrible multidimensional Gauss forms that we can't say anything about. So if I start talking about the proof of this theorem, are there any questions?
Yeah, we have
The short one is not at one of the endpoints, but somewhere in the middle. So what you kind of get T.
So if you put one like, are you saying if I instead of putting it there, I put it like here?
Yeah.
So then that ends up being like the axis line squares situation.
Okay.
So if you're I guess 4 points, if they're in general position, then that's this like super difficult situation that's as difficult as axis line squares. But if they're not, then okay, I'm claiming in some cases you can prove bounds.
Sarah, we have a question what capital N represents in the theorem.
Oh yeah, sorry. I forgot to say capital N is p to the n, so it's the size of p to the n. Well, this should also be capital N squared. Yes, thank you for whoever asked. Yes, thank you, Terry. Yes, that's what I mean. Maybe I should Zoom people can see both boards good.
I have a question about Stradov's result.
Oh, yeah.
So does that C depend on the dimension D? The power of log n?
So it's just in 2 dimensions that we know this. And if you looked at like corners embedded in like 3 dimensions, you could just make a linear transformation. And it might change maybe it'll change like the implied constant or something,
Oh,
but the C is going to be the same thing. Is more water with this better or worse? Okay. Okay, so now I'll start talking about the proof of the theorem. But I'll start talking about the proof of this theorem by talking about, or giving you an outline of Stradov's proof of his bounds for sets lacking corners, but described like in the finite field setting. So Shkredov's argument in the finite field setting proceeds by a density increment argument. So basically, the strategy is to show that, okay, or I think now here I'm going to call it S. If S is a subset of, say, e to the n, e to the n, it has no non-trivial corners, then it's going to be vague here. We can find a structure subset of which S has increased density. And let's say that S has density, it has no corners, and density sigma. So we'll say S has increased density sigma plus some constant times sigma to some bounded power. And the idea is, okay, now you just focus on S on this structured set and so that you can find a structured subset of that, on which S has the same increased density. And so you show that you can kind of only do this as long as P then is large enough. But you can't continue this iteration forever because that density can't grow above 1. So at some point in this iteration, your lower bound on the size of P to the n must fail. And you can unravel this to get a bound on the size of the original set that has no corners. So what this looks like in more detail is, so as in all analytic proofs of Szemer's theorem and original and more general results. We define a multilinear counting operator over the configuration of the pair bound of corners. Make this not look like an L. So if F0, F1, and F2 are functions from e to the n plus numbers, and we set lambda of F0, F1, F2, the average over X, Y, and Z of the corners configuration weighted by F0, F1, and F2. So then, if you plug in the indicator function of a set, which I'll just denote by the same letters as set itself. Then the S is just the weighted count of the number of corners in S. So all corners, not just the non-trivial ones. Yeah, and now just forever, I'm going to set that to be the same as in the theorem. So then we'll divide this by n cubed. And then if you write g sub s for what's called the balance function of s, so just s minus the constant function of density, then the SSS, the weighted count equals then so s equals g sub s plus sigma. So this equals sigma times lambda with constant function 1 as an s plus lambda with g sub s as an s. Now, it's not hard to show using like the Cauchy-Schwarz inequality that this expression, solve this together, is bounded below by sigma cubed. And if S has no non-trivial corners, then this just equals the weighted count of trivial corners, which is just counted by x and y, and then would z equals 0. So this gives alpha, sigma over n when S has no corners. So when S has no corners, since this term is large, like at least sigma cubed, and n is sufficiently large, then this last term must cancel out with this term in terms of magnitude to get something this small on the other side. So the point is that if S has no non-trivial corners, then this quantity must be large. Plus, sorry, erase more.
Sorry, I'm confused.
Oh, sorry.
Yes, because capital S is a set and sigma is a number because it's a density.
Ah,
If I take capital S minus sigma, what's that?
so I should have written down how I'm using capital S instead of just saying it. So I'm using capital S to denote both the set S and its indicator function. So so S is a set.
S is kind of normalized, otherwise it's a special graph.
Yeah, so if S is a subset, also I'm going to denote the indicator function of S by the same letter as the set. Yeah. So yeah, indicator function minus sigma. Yeah, thanks. Should have written it down. Oh, did I forget to do the squeegee thing? Okay, thanks. Yeah, so I was gonna say that then if S, oh, maybe I should wait a second for it to dry more. Our set S has no non-trivial corners. Then size of lambda piece of S has S. It's bigger than some constant times gamma or sigma cubed. And this is provided that n is larger than some bounded power of 1 over sigma. Probably the bounded power is like -2. So then under this assumption, we want to deduce that S has a density increment and some kind of structured subset of fp to the n plus fp to the n. So then what one does is you can show using a few applications of Cauchy-Schwarz that this implies that the two-dimensional box form of S, I'm sorry, of E sub S is large. So what is that? So the two-dimensional box norm of function G to the 4th power is the following quantity. So it's the average over x prime y prime, such that O of g of xy, x prime y, the complex conjugate, g of x y prime, the complex conjugate, and g of x prime y prime. So it's not like kind of immediately obvious that this is actually a norm. But it's not that hard to show. So then from the application of the Cauchy-Schwarz inequality, we get from this that the two-dimensional box norm, P sub S, is also larger, like sigma to the cube times some constant. So then to deduce a density increment from this inequality is not very hard. It basically just requires a couple of averaging arguments. So from a few averaging arguments, you can deduce from this that S has a density increment from the fact that the two-dimensional box form of the balanced function S is large, has a density increment of the form the original density plus some bounded power of the density on a product set. So A cross B in FP to the n cross FP to the n, and with some lower bounds on the densities of A and B. So this is what I mean by like a structured set. It's not just any set, it's a product set. So then the hope would be that you could just run through this argument again, but just looking at the set S on the product set, then get a density increment on a smaller product set within A cross B to run the density increment argument. But this doesn't work And the problem is, basically that this argument I mentioned, just using the Cauchy-Schwarz inequality, is deduced from this, that the two-dimensional box form of G sub S is large. So this implication isn't true in like a kind of density preserving way when you're just working on general product sets A cross B. So to be more precise, we would want to prove that if mesh, let's say it's now a subset of the cross set A cross B, then knowing that the counting operator G sub S is large relative to the size of the counting operator, with all these replaced by the product set A cross B, and which S is supported. So now the balance function, you subtract the constant function sigma on A cross B. So you want to know that if this is large, say bigger than some delta, then it also implies that the box norm of G sub S is now supported on the product set A cross B divided by the same box norm of A cross B is also larger than, let's say, some x power of delta. And the reason why you want something like this is if you don't have something this strong, then if you run through the argument, you get a density increment that gets worse as A and B get sparser. And then you can't close the density increment iteration. Because the reason why this density increment argument works is you only need to apply this like 1 over sigma to the big O of 1 many times to get a density above 1. But if this is replaced by something smaller each time, you're not necessarily going to get above 1. So you don't know that the iteration closes. And so for general product sets A cross B, you're not going to have this in general. You won't have this while we're running out of time for general A cross B. Erasing than I thought I would. So basically what you need for this implication that we want to be true is you need that A and B are sufficiently Fourier uniform for this to be true. So what Shkirov does is he introduces a pseudo-randomizing step into his argument that shows that if you have a density increment, I said from A cross B, then you can actually localize to a product of two cosets of the same subspace of fp to the n, on which you still have a density increment just about as strong, but you can show that A and B are sufficiently Fourier uniform. So this means that A and B have no large nontrivial Fourier coefficients. And the way straight up proves this is basically by using an energy increment argument to partition the space fp to the n across fp to the n. Okay, so now with my remaining just 3 minutes, I will try and describe to you how the argument works for L-shaped configurations instead of corners. So what's different for L-shaped configurations? Different for House. So the broad structure of the proof, as doing a density increment argument, where you first show that your set that lacks L's, its balance function must have some large directional uniformity norm, proving an inverse theorem for that norm, and then getting a set where now again you want the constituent parts of that set to be pseudo-random, so you have to do a pseudo-randomizing argument. These are all present in the argument for L's instead of corners, but kind of each step of it is significantly more complicated. And one of the reasons for that is that the obstructions to uniformity for L's are not just product sets and skew product sets, but also sets the following very general form. The sets of the form X and Y. And back to the end, where some element gamma of fp to the n, its dot product of x equals, sorry, dot product of y equals some element of fp for all gamma in some finite set depending on x. So this is basically the union for each x of some subspace. With the subspace, kind of any arbitrary subspace of fp to the n. And so to finish the sentence, so sets of this form do not, oops, this is still it, so do not have close to the number of L's as a random set of the same density. And basically all the additional difficulty of L's over corners is kind of dealing with this sort of obstruction to uniformity. So as an example of one of these sets, you can consider the set of x and y, such that x dot y is 0. So this has density, okay, as long as like n's big enough. This is density about 1 over p, but it has around n cubed over p cubed, many L's, while a random set with high probability has about cubed over e to the fourth many else. So it's have to take sets like this into account. You can also take instead of x just some randomly chosen vector in G. And with high probability, these same two bets will hold. So these sets can be very general and still cause problems. I'm not done with this one. So I'm now slightly over time, but I want to say some of the ingredients that go into each step of the proof. So I'll say that the inverse theorem or the directional uniformity norm encountered is either the one I'm about to write down or kind of skew versions of it. Is the average over x, y, h1, h2, and h3 of following quantity. So the multiplicative differentiation operator, I'll write down in a second, with 0 h1, 0 h2, and h3 0 applied to G. So call this the eighth power of the star one norm. So here, delta sub some element of your group of another function of that group. This equals g of x times g of x plus h bar. So I think I mentioned earlier that so this is a two-dimensional uniformity norm with three differencing parameters. And how hard this is to analyze depends on what vectors you get here that are multiplied by h1, h2, and h3. If the three vectors are all in general position, then the analysis of this norm is like totally intractable. It's like the norm that shows up for these three-dimensional corners and axis line squares. When all three of these line align, you basically have a two-dimensional U3 norm. And that's already been studied in work with Prendeville, and that's basically understood, at least I think to like the same extent the U3 norm in one dimension is understood. So if these three are in general position, like it's impossible if they're on the same line, then it's kind of known. But when they lie on exactly two lines, this norm has kind of the structure of a U1 cross U2 norm. And it turns out, kind of with a lot of work, you can analyze this norm well enough to prove a suitable density increment needed to get bounds for sets without L's. One thing that you need in the proof, it turns out, is an application of the transference principle. Basically, because you need a density preserving version of the U2 inverse theorem on a sparse, like random set. And yeah, so I've gone okay sufficiently over time that I now feel bad continuing to talk. So I'll end here.